Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everyone. Lecture 5 Organic Chemistry 1. In today's lecture, we will cover some problem and solution to check on our understanding and our knowledge on the vocabulary of the organic chemistry we gained so far. The first problem, sodium borohydride NaBH4 is a reagent used in the conversion of aldehydes and ketones to alcohols. It can be made by treating boron BH3 with sodium hydride according to the following equation. A. Draw the Lewis structure for the borohydride. We used to do the following. Number 1, count the total valence electrons. So 4 hydrogen, 1 boron, and 1 charge. 4 times 1, 1 times 3, plus 1 charge give 8 electrons total. Number 2, bonding structure. Boron in the middle and 4 hydrogen around. Check on the octet or dot for hydrogen on the outer elements. Hydrogen 2, 2, 2, 2, and the boron 8 with negative charge. So we have 8 electrons here and we have 8 electrons total. That's fine. Where is the charge? Recall formally charge equal valence electron minus non-bonding electrons minus half shared electrons. For the boron, we have valence electron 3, no lone pair, minus half, we have around 8 electrons. So total will lead to the negative 1 charge. For the hydrogen, 1 minus 0, half 2 equals 0. So the charge will be located on the boron. What is the shape of borohydride ion? The best arrangement of BH4 minus is therefore the same as CH4. Since the steric number 4, BH4, so AX4, steric number 4, and the hybridization will be S and B3. Since we have 4 bond, we have 4 sb3 orbitals. sb3 means that we have electronically tetrahedral, and since it's AX4, 4 sigma bond, means that molecular shape will be again tetrahedral. Draw an orbital picture of the attack of H- on boron. Which are the orbitals involving the overlap of the bond formation? For the boron BH3, the hybridization of boron is Sb2, Sb2, with empty b orbit. So the hydride ion will attack this empty b to form sigma bond and transfer this boron hybridization from sb2 to sb3, hybridize, transferring this from trigonal planar to tetrahedral structure. With negative charge. Problem number 2. Propyne can be deprotonated twice with very strong base, which means that the base removes the 2 protons labeled by arrow, this hydrogen and one of the hydrogen of the CH3, to form propyne dianion. 2 resonance forms of the anion can be constructed in which all 3 carbons have Lewis octet. Draw both structures and indicate which is the minor and major. Important one. To draw the Lewis structure for that dianion, we count total electrons. In this formula, we have 2 hydrogens, 3 carbons, and 2 charges. 2 times 1, 3 times 4, plus 2 charges gave 16 electrons. Number 2, we do the bonding structure. So carbon connected to carbon according to the way the problem gives this structure. Okay, carbon, and then this carbon has 2 hydrogens. Done. Okay, now be sure that you have octet or dot for hydrogen on the outer element. So we give these 2 electrons, since it said already 1, 2, 3. We give this one 1, 2, 3, 4, 5, 6, since we have only 1 bond. Count the number of electrons: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10 and 6, 16. We use the whole 16 electrons. But still, this carbon has only now 4 electrons. To do that and correct the structure, we took 2 electrons from here and formed a double bond to give us this structure. Still, this carbon has only 6. 1, 2, 3, 4, 5, 6. We take another 2 from this carbon and form a double bond. Now we have 8 on this carbon, 8 on that one, 8 on this one. All right. So this is okay. We have reached the right connections. But where is the charge? Again, formally charge equal valence electron minus non-valence electron, non-bonding electrons minus half shared electrons. For this carbon, we have 4 valence electron minus 2 non-bonding, 1, 2, minus 2. Then we have 1, 2, 3. We have 6 electrons in here. Half of it, 3. 4 minus 2 minus 3 is minus 1. So this carbon has formal of negative charge. Come to this one. This carbon, 4 valence minus, does not have lone pair, 0. Number bonding, okay, 0. And how many bond? 1, 2, 3, 4. Each with 2 electrons, so it have 8. 4 minus 4. Formal charge of this carbon, 0. Come to that one. Carbon 4. Yes, we have 2 electrons non-bonding, 2. How many bonds? 1, 2, 3. So half of 6 electrons in bonding, okay, minus, so this one has minus. If we look for the resonance structure, these two could move from here to that, to the middle, and this will break this carbon, forming this minus 2 and form of that. Minus 2, but minus 1 is much more logic to be formed, so this is major and this is minor. Okay, we go and see for lower charge. So this is 2, but this is 1, this is 1, will be the major. Propyne dianion adopts the following hybridization: carbon sp, carbon sp, carbon sp2, in which the CH2 terminus is sp2 hybridized, unlike the metal anion in which the carbon is sp3 hybridized. Provide an orbital drawing of the dianion to explain this preference in hybridization. This carbon is sp, so we have 2 pure B and 2 sp orbitals. This carbon, again, sp, so we have 2 pure B's. This is 1, 2, and we have 2 sp orbitals. This p orbital has an electron with electron, so we have here pi bond side by side. And we have here pure B, 1 electron, so we have pi bond. We have Sp with Sp from carbon. This is again sigma bond. This lone pair are in Sp hybridized orbit, and this carbon has a negative charge. Here we have 1 Sp left, will come with Sp2 orbit from this carbon, which as mentioned is Sp2, so it has only 1 p orbit. Recall that this carbon has a negative charge, so has 2 electrons. two electrons with one electron with one electron. If we make this p orbital open as such, so we have four electrons delocalized over 3p orbit. That gave high stability. Delocalization, the results of delocalization is stability. That's why this carbon preferred sp3 hybridized to actually let these two electrons to be as such open to the other 2p orbital. For the CH3, we have total of 4 electrons on carbon, 3 on hydrogen, and 1 for the charge. So we have 8 electrons bonding, carbon, bond, bond, bond. So we used 6 electrons, but we have 8. So we give this 2 electrons, okay? And this will be a negative. This is belong to AX3E, steric number 3 plus 1 is 4, so it's sp3, and sp3, as we know, electronically tetrahedral arrangement of atom is trigonal pyramidal. But what about the hybridization of the carbon in the methyl cation? Total valence electron carbon 4, 3 for hydrogen, and since we have a positive charge, so -1 for the charge. So we have total of 6 electrons. Bonding structure, it's carbon, carbon, carbon. So we used the 6 electrons. We know that carbon will have a positive charge. It's belong to AX3, steric number 3, so it's sp2. If it's sp2, so it will form trigonal, planar trigonal. Okay, and we have pure B empty, and the carbon has a positive charge. So remember that this will be planar with empty B. That's the carbocation, and it is sp2 hybridized. 3 Lewis structures for the cyanate ion NCO- are shown below using formal charge considerations. Which of this structure would be best? Please explain your answer. Again, recall formal charge, valence electrons minus non-bonding electrons minus half shared electrons. N O carbon oxygen. A formal charge on this nitrogen, valence electron 5, 6 non-bonding electrons, minus half, we have only one bond, so it's 2 electrons, and that led to minus 2. So the nitrogen will have minus 2. Carbon 0, and the oxygen plus 1. Here, nitrogen, you will find it minus 1, here is 0, and here is 0. Here, find it 0, and you'll find it 0, and here is minus 1. Here is minus 1, and here is minus 1. but oxygen is more electronegative than nitrogen, so it will prefer to carry on the negative charge, and this one will be the most important I would measure in the resonance structure. Here is second one, and this one will be the least, where nitrogen carries two negative charge. The best structure has the fewest formal charges and has a negative charge on the highest electronegative atom. See you in the coming lecture. Bye bye, everyone.